So once again, linear operators are matrices. They are also transformations, and we're talking about transformations of the plane, which means our space is R2, and our matrices are 2 by 2. So our function then is from R2 to R2, and A is a 2 by 2 matrix. So at the same time, we use the same notation, by the way. So we use the same letter A to describe A as a linear operator. See that notation is A column R2 to R2. That we're talking about a function from R2 to R2 vectors, two-dimensional vectors to two-dimensional vectors, and it is a linear operator. At the same time, it is also a 2 by 2 matrix. Okay, it's the same thing. Certainly, notation is slightly different. We either write it A of x, that's the standard notation, name of the function followed by the name of the variable in parentheses. That is how we write like this. That's how we write functions. We also write it like this when we speak of matrix multiplication. We write them just side by side without the parentheses. So once again, functional notation followed by the matrix multiplication notation. Okay, so and that way, for a short while, we'll concentrate entirely on 2 by 2 on this situation, which is right here. So everything is about the plane. Okay, so so we have defined the determinant. Still to be figured out what it is good for, and then we also define these two things. The kernel and the image. The solution set of a homogeneous system is called the kernel of that matrix, and the image is the set of all possible outputs. So it's more complicated than it sounds. Well, it is less complicated than it sounds, especially if in this two-dimensional situation. That's a good example right there. The transformation, I hope, is clear what it is doing here. It takes the plane and collapses it to that red line. Okay, so like this. Okay, so that's how you would describe A as a transformation. Then whatever matrix is we saw, and I'll pull it out in a minute. But you can also tell what the image is. The red line is the image. So every x will end up where? On that line, and vice versa. Every point on the red line, it has some bunch of x's going there, just like those orange lines indicate. And that's first, the image of f, of that matrix or transformation is the red line, and then the green line is the kernel. It is what values, what vectors on the xy plane, the domain. So this is the domain we're talking about. The domain is this, and the range is somewhere else. I just put it in the on the same xy plane, but they are two on the left, are two on the right. They're different, two different copies. They all end up. Where are they? And they are along that perpendicular line. The green line is perpendicular to the red line, and our projection, given by those orange lines, is perpendicular or orthogonal projection on the red line, and therefore the line that is perpendicular through the origin will end up entirely inside of the origin, right? Like you collapse and you see where what everything goes to 0, and so that is the kernel is that green line. Okay, so let me before we go back to examples. Let's look at the well. Let me make this statement. Theorem. Part 1. The kernel is a subspace. Okay. So it requires proof, but it's not too complicated. The linearity of our function demonstrate that it is the kernel will be a subspace. Okay, And let me make this two statements, the second one too. So is the image. Is a subspace. So these are two theoretical statements, but so before we address them in any kind of generality, if we just take it in the form of our two-dimensional case, we're speaking of subspaces. The kernel is a subspace of the domain, while the image is a subspace. Let's be specific here, of the domain. And this one is the image is the subspace of the codomain. Either one of them is two-dimensional. So what subspaces of a two-dimensional space, you know?
What space of a two-dimensional space?
Yeah, subspaces of a two-dimensional space.
Lines.
Lines, not points. 0, 1 point. And the third option is what? The plane, yeah. So same for both of these two. The answer is in the two-dimensional case, it will be always the same. If you want to put it in the form of in a kind of hierarchical way, then it will be point line, any line through the origin. So not any line, or the whole plane. Okay. So if I try to put this in the kind of a kernel. So two-dimensional case, the kernel will be 0, a line through 0, or the whole plane. And then I do the same for the image. So once again, 0, a line through the origin, the whole plane. We're not talking about the same. However, once again, they're subspaces of two different spaces. Even though that space in either case is a plane, there are two different copies, and so they should not be confused. In the future, linear operators could be between dimensions of spaces of any dimension. So it is a coincidence that we're looking at domain and codomain of the same exact dimension. So that's a little bit of a confusion, but it is the lowest dimension where things start to become interesting. So once again, they do not overlap, they do not equal to each other or anything like that, but there might be there might be a match. Do you see a match between the three cases on the left and three cases on the right? Well, the picture, what the picture tells you.
Where they meet, is that the origin? Is that reunion, or you look for something else?
There are three cases for each. So how many total cases do we have? Is it 9? You would think, but let's think about it a little bit more.
For example, like if the solution set is 0,
Yeah.
the image can't be a line, right?
That's right. So the solution set is 0. So the solution set is 0. So there is only one 0 that goes to 0. Let's pick that's a good thing, correct way of thinking. But let's pick something simpler. Let's suppose the answer is 0. Let's say the kernel is everything. So let me take the last one. The kernel is everything, right? So that matrix takes everything to 0, right? So that's the kernel. The kernel is whatever goes to 0. Suppose everything goes to 0. Okay. So what about the image then? So if the whole plane is the kernel, what's the image? Everything goes to 0. What is the image? 0. Okay, here it is. That's the match. And if the image is 0, that means the kernel is everything, right? So it goes both ways. So they're matched. So if one, then the other, we'll already know that there will be fewer than 9 cases. Okay, so can you suggest anything else? And now let's look at the other case. If suppose the kernel is 0, which means that is trickier. If the kernel is 0, which means that there are no vectors that go to 0 other than 0. Okay? Remember what that means? Well, for one, it means that remember the two basis vectors do not become multiples of each other, right? Because if they were, then you can create a linear combination of them, and that vector which is not 0 will go to 0, right? So that's part of the discussion that we had yesterday, and then well, but frankly, it would require some extra justification, but an actual proof. But this is the match. Where's the word plane? Where did it go? Okay, so if the kernel is 0, then the image is the whole plane. Remember rotations. Remember those rotations, stretches, and rotation stretches and flips. All of them are preserved. The only thing that goes to 0 is 0, right? And they do not. We do not lose anything. So the image will be everything. So you rotate a piece of paper. Well, the image is the whole plane, right? Or you flip it, or you stretch it. It's still the whole thing. So you're not going to lose anything from the image. So and vice versa, if that is the case, then well, certainly the kernel will be equal to 0. But that will require proof. Well, the whole thing will require proof. So the third match is, you can guess it, a line through the origin will be matched with a line through the origin like this. That is the case that we saw. That case we started with, this one, is the third, or the second case, right? So the image and the kernel, 2 lines. So how would you describe these matches, if you can? Can you describe it in one sentence? So this is n equal to 2. How about we look at dimensions? The dimension of the whole plane is 2, dimension of the line is 1, and the dimension of one point is 0. Okay? The sum is up to 2. So 0, 1, 2. And so the match, they have complementary dimensions. Okay? So the image and the kernel have complementary dimensions. By which I could put it in algebraic form like this. Well, the image first. I am, that is my image. So if our linear operator is A, then I am A is its image. K-E-R is the kernel, and they add up to n. So complementary to n. One is growing, the other one is declining, roughly speaking. So as you can see, there are totally n plus 1 cases. N plus 1 cases. So in this particular case, we have 3 cases. The only possible dimensions of if one dimension is known, then the other one is known too. Okay, so that is the match. You can even try to describe it once again for dimension 2 you can these we have three classes. So let me try to put it once again. If I try to put these two matched up. So kernel 0 align through 0, the whole plane, and they are matched up with the images. So the whole plane, align through 0, and 0, 0.0. Okay, so that is the match, the three cases. Let me call them 0, 1, and 2 according to the dimension of the kernel. Okay, I could probably even try to describe them in one word. Okay, so the first one is the kernel is 0. So have you heard the word bijection? A bijection, anyone?
I don't know what
One-to-one onto.
Oh, okay.
So it's just a word, a convenient, fancy word, but if I'm putting it here just to have one word description of what we're facing. So whenever the kernel is 0, it means that bijection, so there are no collapses. It is one-to-one onto a function. Okay. It is also another way to describe it is invertible, because it has the inverse. So we'll get to that shortly. A projection, the second one. So my image is a line through 0, and we make our orthogonal projection of the whole plane on that line. Okay? And the third one I will describe as a collapse, because everything goes to 0, to one single point. Okay? And then you can imagine that in higher dimensions what can happen, how this becomes more complicated. So n dimensions, you have n plus 1 rows in this table. At the bottom, at the top rather, it will still be bijection, right? So the kernel equal to 0, that's still a bijection. And then there at the end will be still collapse at the bottom. To everything goes to 0. And then dimensions go, you have a bunch of projections on spaces of different directions. So either it is n minus, so you start with n, that's the first line, n minus 1, n minus 2, minus 3, and you project on lower and lower dimension spaces until at the very end you project on the point, okay, on the origin. Okay, so these are the cases. What about the determinant? What does it have to do with the determinant? If you remember our initial discussion where determinant came from into the two-dimensional cases, here somewhere, we solved. I remember how here it is. We solved our system of linear equations 2 by 2, and the determinant appeared. You can see that case 2. Here we have only two cases. One is determinant is or is not equal to 0. Okay, so when it is not equal to 0, we have what those three ideas, three types of transformation: flip, rotation, and stretch. Those are bijections. Okay, so that is when there is no any kind of projection of collapse, and that's the meaning of the determinant. It is a determinant of A is not equal to 0, or in these two cases it is. So if determinant is equal to 0, we cannot distinguish between the cases other than the very first one, the nice one. Determinant is not equal to 0. Okay, so that you know then that we are in that category. And remember the terminology we used was slightly different. It was singular and non-singular. So this one is singular. So it indicates collapses. And collapses if two vectors come together and equal to the same one. Okay, what does it mean? It means that you cannot invert it, because two vectors come together to the same. If you try to reverse the arrow, you'll have to split, which is not a function anymore. Okay, so whether it is a function of numbers or of vectors, the rule still holds. You've got to have a bijection one-to-one onto in order to have the inverse. Okay, so So that is the something to discuss, but I think I'll do a few examples, and let's do a few examples first. So the one that we started with is this. As you can see, projection. Both of the lines appear. The determinant you can see at the top is equal to 0. You can certainly vary. There is nothing especially important about this one. It is just a projection that is not obvious from what the matrix looks like. Because you can guess when, say, if I put here 0 and 0. Okay, so then it is predictable. Our image is still the red one. Or did I do it the wrong way? Might have. Hold on a second. No, that's what I meant is this. No. This one. What did I have in mind? Okay, let's just start over. The projection, suppose I want to do projection on the x-axis. What does the matrix look like? So once again, the two columns are the images of the two basis vectors. So the first basis vector is 1, 0. Where does it go? Under the projection on the x-axis. So everything goes like this. 1, 0. Where does it go? It remains the same. So in the first column, I put 1, 0. Okay, and in the meantime, what happens to 0, 1? It becomes 0, 0. So we have it, right? So the first column is 1, 0. So that's what happens to 1, 0. The first basis vector, the second vector collapses to 0, and that is our matrix. And look now at the graph. First of all, the output on the right, to confirm it is the x-axis, right? And then the image, these two lines, where they come from, will still to be discussed. But the image is the red line, and the kernel is the green one. It is the projection, right? Everything is all the multiples of the 0, 1 will be on that in the kernel. So, okay. So what else we might have? Determinant is equal to 0. Let's try. What if I put? Let me see what else I want to look at. So 2, 0. If I put 2 here, it's not a projection. This one is a projection with a stretch. So, but it has the same image and kernel, right? So I put a 2 there. So 1, 0 goes to 2, 0. So there is this horizontal stretch. But as you can see, it does not affect the image and the kernel. And the determinant is still 0. Okay. So what if I put 4 here? What if I put 4 here? What's going to happen? There will be a horizontal stretch and there will be a vertical stretch. Okay? Okay, so to confirm that, and then what does altogether, what does it do? It will turn these circles into what? But bunch of ellipses stretched vertically because the horizontal stretch is smaller than the vertical stretch. Okay, but there is something misleading about that's exactly what you see here. There is a little bit misleading about it, and what I mean is it is you cannot see exactly what happens to every vector, and you might think, what happens to a vector? What happens to the vector? You know what's happened to what will going to happen to the horizontal vectors? They will be stretched horizontally. Vertically will be stretched vertically. You can see it, right? But what about diagonal ones? So the horizontal will be stretched by 2. You can see it vertically by 4. What about diagonal ones?
When you do Pythagoras, kind of?
What?
When you find, well, no, never mind.
Will they be stretched by the tangents?
It was a trick question. They will be, what do you think the trick is? They will be stretched by what else? Well, try to imagine a vector like this, and then try to stretch it horizontally, then vertically. What's going to happen? Same
As
way.
long as you don't change the angle, it should be the same, right?
Why wouldn't it? Well, it's again stretch. It changes. If you stretch this vector horizontally, it will change the angle.
Oh, okay.
And then if you add a vertical, then you might not come back if it's not the same number. So then circles are misleading in that, in the sense we cannot see we don't see the rotations. Okay. So I think I have it somewhere else. Not this one. This must be it. So that's exactly the right example here. 2004. And you can see that if you look carefully at the colors, you can see what happens to the vectors. You see? And the colors are bland, but you can see the first one is kind of a brown, and you can see what happened to it. It got rotated. We know that the length will be longer by some factor, but it is important to realize that there's also rotation. Okay, so even though it is a diagonal matrix, it does not mean that it is pure stretch. So disproportional stretching causes rotation as well. Okay, so what else? Let me try this one. If I put here -1, what happened? We still have, well, let's put -2 here. -2. So we have the same exact. We have the same exact ellipses. I had 2. I had ellipses. I have -2. I still have ellipses. Is there any difference? We flipped it. Can you see it on the graph? I mean, yeah, I flipped the ellipse. It's the same ellipse.
Are the arrows going
The
the other
arrows,
way?
right. If you watch the arrows, then you can see that they have reversed. So if they used to go counterclockwise, they go clockwise now. You see it? Okay, so that's what flip does. Did you see anything that has changed?
Red and green.
No, I don't think so. It's the same.
Was it not green and that gets vertical and then red horizontal? Or did we change that?
Well, let me show you again. So if I put 2 here, over here I put 2, and see watch the changes. It didn't reverse, did it? What has changed? Well, let me do it again. See the change? No, it's the same. The picture does not change. You have to look elsewhere. The determinant. The determinant in this here it is 8, and over here it is. What happened here? I pushed something. 8, or if I put here -2, it will be -8 naturally, right? So in other words, negative determinant indicates a flip. Is technical term. It's called the reversal of orientation. So orientation meaning that the 2 basis vectors. It is still a bijection, so the 2 basis vectors will remain basis vectors. They might change the angle between them, but they remain like this. And what changes is which way you go from the first to the second. Either you go clockwise or you go counterclockwise. So as you can see here, you go from E1 to E2. You go clockwise. That's counterclockwise. That is the original arrangement. But what happens to their images? They become opposite. And well, I probably should be able to get it here if I put once again -2 over here. -2, as you can see here, the blue one horizontal. It remains horizontal, and well, I'm not sure if that will be visible actually. Okay, so you actually can see the flip, right? The flip is visible. Okay. So we have seen one collapse already. Well, so something more exotic. Let me see what I have here. -1, -2, -1, -1, -2, 1, 1, and -4. Okay. So it is tempting to say that we have a stretch in a diagonal. If you look at the circles, it appears that what you have done, you stretch them in the diagonal direction, right? That's what it looks like. But we know that it already is not the case necessarily. Stretching is really a very, especially when you do simultaneously stretches, it is not a good way to describe it. Rotation is. So imagine that what has happened is here, you can imagine what how this transformation has been accomplished. You stretch it horizontally first and then rotate. Then we have two transformations that are the simplest one. The simplest ones are rotation, flip, and stretch. Stretch in one direction along one of the axes, say the x-axis. Okay, so that's what this is, and so those two lines do not mean any image in kernel anymore, right? We are talking about the bijection, so there are no projections, and the kernel is 0, and the image is everything. So those lines have different meanings altogether. They indicate the direction at which there is a stretching or shrinking. Okay, so those called the eigenvectors. So that is one way to interpret it is exactly that. So we have you can see them if you look at slightly to the right at the top. They say real eigenvalues and followed by eigenvectors. So eigenvectors give you the direction of those two vectors, 2, 1 and -2, -1. Okay, no, the 2, 1 and 1, 1. Right, the green one is 1, 1, and the red one is 2, 1. Okay, so those two are the eigenvectors, and then the eigenvalues are the stretches. So those you see those numbers -2.5. Those are the stretches in those two directions. So they actually happens to be uniformly stretched along those two directions. But it should be understood very carefully. It doesn't mean that we stretch in that direction. It means that there is a stretch. The result of our transformation is a stretch along that line. It means that elsewhere something else might be happening, something more complex. But along that line, everything is very simple. It is a pure stretch. Okay, so that's the meaning of the eigenvector. It is the direction at which there is a stretch. Elsewhere, it might be something else. So, for example, rotation does not have eigenvalues. Eigenvectors, because there is no stretch in any particular direction. Once you turn, nobody's stretching anywhere. In fact, there is a stretch. It just happens to be complex. A complex number. So you stretch by a complex number, if it makes any sense. So have you seen complex numbers? Imaginary and real. Oh, yeah. So unfortunately, that what you face here, we're gonna look at it at least a little bit, is that you end up with a quadratic equation, and then the quadratic equation might have complex roots, and then what are you going to do about it? Nothing. So for the time being, we are just looking at concentrating on the kernel and the image as the simplest way to analyze the transformation. Okay, and I have one more example, and that is this: -1, 2, 2, and -1. Okay, so what it means exactly might not be clear, but there is a, so -1 to -1. So it appears once again it is a stretch, and it appears like a rotation, or stretch in the diagonal direction, but the reality is, I hope I have it here, that is pretty much close to what I had in mind. It's called a shear. So let me have the same, so that's not exactly the same, so let me change -1 to 0 and -1. Okay, so you can see what has happened to the square. So the original plane had a square drawn on it, from -1 to 1, that's the square. And then you can see what has happened to that square. That's on the right. That is like a shear, or like a what is it, like take a deck of cards and push it, right? So it becomes a parallelogram. Okay, so that's a kind of one of more complicated linear transformations. Even on a plane, you can have things that are somewhat complex. Okay. And then naturally we have the rotation. So we already talked about that. Rotation and shrink. Okay. Okay, so examples. Now, what else? That was something. So we have some depths here, and one is why the kernel is, and the image is a subspace. Okay, so let's prove this theorem. It's not too challenging. So suppose V is the kernel of A. It means it's all of those x's in R2. The A of x of which is equal to 0. Okay. Now remember the definition of a subspace. It preserves linear combinations. So let's take x and y. Suppose x and y belongs to V, and now we need to demonstrate that, say, ax plus by also belongs to V. So that's what it means to be a subspace. It preserves linear combinations. So it contains linear combinations of its elements. Okay. So in a particular case, really no need to make it two-dimensionally, because the proof itself is purely abstract and applies to anything we can think of. So we have a transformation A from Rn to Rm, and we're looking at its kernel. It is really is proven in one line, pretty much. So how do I demonstrate that this thing belongs to V? I just apply A to it. So we just consider A of ax plus by, and what I do is I apply the fact that A is linear. Remember what it means for a function to be a linear operator. It not remove, but
Put A inside of the
right, outside. So A is outside and B is outside, and the summation outside. I could take take it out. Okay, so it is A. So I'm using the linearity of A. It will be ax plus b ay. Ay, yes. Okay, so that's the linearity. It preserves linear combinations once again, and then what happens? X belongs to the kernel, and y belongs to the kernel. So ax is what? Zero. Ay is 0 as well, because they belong to the kernel. So I have A0 plus B0, which is equal to 0. So indeed, this new element, ax plus by, belongs to the kernel. Okay, so that's the whole proof. So just the computation I'm using, I have used I have used the two definitions, the linearity of the definition of a linear operator and the definition of a definition of a subspace and the definition of the kernel. So things kind of there are a few things together. So it's slightly more complicated, but not really by a lot, proving that the image is also a subspace. Okay. Any questions about this? So this one was still to be revisited. This classification. So the image and the kernel have complementary dimensions. For the time being, we'll just rely on on what you have on the left at the bottom. The classification of the lines of the three cases. Only three cases in this two-dimensional 2x2 case. And they are classified very nicely. What I want to look at right now is what I just mentioned a minute ago is the inverses. Think about this. If A is a bijection, it means it is the same word pretty much. A is invertible. Oops. A is invertible, so there is such a thing as A inverse as a function. A inverse. So what is it good for? Then to solve AX is equal to B, what do? We just use the inverse. So X is equal to A inverse of B. So this is new to you probably, but for numerical functions you saw something like that in calculus and pre-calculus. So a function is one-to-one onto, it has the inverse, and then you can use it to solve any equations. Right? How? By using the inverse. Hypothetically, if it might remind you of something. If say e to the x is equal to 3, then x is equal to ln 3. Okay, so because we know that the exponential function is invertible and the inverse is the logarithm, and so we can solve these problems. But that's why we designed this function, so which will solve us all of these exponential functions. And vice versa, if you have a logarithm, its inverse is the exponential function, and you can simply solve it in that manner. With linear functions, things are simpler, and but we have to examine it, and once again just look into functions again. It must have been a while since we talked about this a little bit, about functions and inverses in particular, but it is all defined. Remember when it was a while ago. It's all about compositions. Okay, so to understand inverses, we need to understand composition. So if our function, our linear operator is invertible, we can solve all the, not only we can solve one system of linear equations, we can solve any system of linear equations no matter what B is, right? Because we already have, it's the same matrix. Okay, so we solve a bunch of them right away. Okay, so but we cannot understand inverses and bijections without compositions, so let's just look into compositions. So compositions of function of linear operators. I have the interpretation of linear operators as transformations helps, because if you think about it as a transformation, then you can think of it of them carried out consecutively. We have used that expression many times. Shrink, rotate, and flip. Okay, so consecutive operations. That's what compositions are. And the notation is, remember, this is so f g f from R2 to R2, g from R2 to R2. Okay, we can compose them together. F, well, technically in the opposite order. G circle F from R2 to R2. It goes like this. It goes from the beginning to the end like this. This is my composition, right? G circle F. So it is, we are reading from right to left, from right to left. So it's F first, then G second. Okay, and what it is, we have a new function. So two functions are given, applied consecutively, and it gives a new function. Once again, from R2 to R2 just happens to be, and we got to understand certain things about it. And one thing is, if these are linear, if f g are linear, oops, f and g are linear, then so is their composition. Okay, so it's a composition. Proving it is very easy. Remember, I'm not gonna just let me just say it. So remember a linear function. We just mentioned that linear operator preserves linear combinations. So if f preserves linear combinations, it transfers a linear combination to g, which also preserves linear combinations. So altogether, that two consecutive operations will not do anything to linear combinations. It will be still a linear combination. Okay, so there you go. The composition of two linear operators will be a linear operator. Yes. So if f and g are linear operators, then so is g composed with f. Okay. Then the crucial thing is then if these two are in fact linear operators, they are represented by matrices, 2 by 2 matrices. Then so is this one. Want to guess how to find that matrix?
Determinant?
No.
Do you multiply the G matrix times the F matrix?
Yes. That's the thing about linear operators and their matrices. Turns out, to compose two linear operators, all we have to do is to multiply their matrices. And so this is G times F. Okay, so matrix multiplication. It is, in fact, if you think about it, matrix multiplication was called multiplication. Really, it is just a word, so that it resembles other multiplications. But you don't have to call it multiplication. You could just as well call it composition. So it is just the question is, how do we compute the composition of two linear operators if we know they are linear, if they are matrices? And the answer is that algorithm that we have. Just to refresh your memory, how we do 1, 2, 3, 1. Cross 1, 0, 1, 2, multiply row by row, row by column, right? And that is how we compute composition. So this will be 3, right? Then what do I have here? The next entry, 1, 2, 0, 2. What do I have here? 4. And the next entry is 3, 1, 1, 1, which gives me 4 again, right? And then finally I have 3, 1, 0, 2, which gives me 2. Okay, so in other words, that is how we compute compositions. It's well, I guess I'm out of time. Okay, so there will be homework again later on.